In this video, we'll look at the product rule. The product rule is a shortcut for differentiating a function defined as the product of two functions. So let me caution you, curvy road ahead. Okay, be careful. If f of x is defined as the product of two functions u and v, then it is not true that the derivative of the product is the product of the derivatives. Okay, that is not true. What is true is that if f is defined as the product of two functions u and v, then the derivative of f is defined as this sum of derivatives, where we're basically notice that we're moving the derivative from one of the functions to the next. So the way I think of it is that this is kind of a democratic process. Every function gets a derivative, and then you sort of add them together. So it doesn't matter what order we perform this operation in, but notice that the derivative of f is going to be the derivative of u multiplied by the v plus u multiplied by the derivative of v. Okay? So each one of the constituent parts of f gets a derivative, and then you sort of add them together. This is the product rule for differentiating f, which is defined as the product of two functions. Let me prove to you that the product rule actually works. So notice that I've written f as the product of two functions u and v. These are generic, so they could be anything. That way this will work for any function defined as the product of two other functions. Now, I'm going to go to the definition of derivative, right? Remember that the derivative of f is defined as the limit of the difference quotient. So let's go ahead and do that. Notice also that f of x plus h in this case is going to be, well, given by this up here, except remember that what I'm going to do is replace all of the x's by x plus h. So this is going to be equal to u of x plus h multiplied by v of x plus h. Okay? And what I'm going to do is take this value and put those into the difference quotient. So let's go ahead and do that. So when I do that, I get the limit here as h goes to 0. I have a big difference quotient here. And up here on the first part is going to be f of x plus h, which again we saw is given down here. This is u of x plus h multiplied by v of x plus h minus f of x, which is u of x, v of x. Great. Okay, so now what I'd like to do is massage this a little bit so that it works out in the way that I'd like. So I'm going to, perform an operation that you see a lot in mathematics, and that is I'm going to add something in and subtract that same thing back out again. And of course, when I do that, the overall effect is equal to 0, because if you add something and subtract that same thing, of course you get 0. So here's what I'm going to add in and subtract out. So inside, well, in fact, in the numerator here, I'm going to add in u of x plus h multiplied by v of x, but I'm going to subtract out that same thing. So I'm going to subtract out u of x plus h, v of x. And of course, when I do that, if I add that in and subtract the same thing back out again, it's going to add up to 0, but it's going to allow me to manipulate my difference quotient in the way that I'd like. So let's go ahead and put those values into the difference quotient. Okay, so now I've put those values in, and I've left the colors the way they were so that you could see where things appear. That is, notice that I sort of rearranged things. I started with this u of x, v of x over here, paired up with the positive u of x plus h, v of x in black. Okay, that's right here. And then I have this second term here, u of x plus h, v of x plus h, paired up with the negative little black thing that I added over here. It's kind of scrunched, but that's u of x plus h and v of x. Okay? So that's a long quotient here. It looks like there's a lot of stuff here, but you'll see that things factor out in a nice way. In particular, notice that for these first two pieces, notice that this first little chunk here has a v of x that's common, right? So I can actually factor out a v of x in this little difference. Notice these two. Okay, so there's a v of x here and here. So I'm going to factor that out. And similarly over here, for this other little difference, I have a common u of x plus h. Here's a u of x plus h, but here's one as well. So I'm going to factor those out also. So if I factor the u of x plus h out of here and the v of x out of the first part, then I'll be able to go one step further. So let's go ahead and do that. In particular, let me just write these out. This is equal to the limit as h goes to 0. And of course, there's an h down below the entire thing. But what I have here is that, again, I'm going to factor out this v of x. There's a v of x outside of here. What's left over is a u of x plus h, right, minus u of x, plus, if I factor out the u of x plus h over here, so this is a u of x plus h, if I factor that out of this second part, you can see that I have a v of x plus h left over, minus a v of x. And everything's over h. Okay, so I've just factored out these parts. Now, what I'm going to do is, these are all over h. So that means since there's a plus sign in between, I can break this up into a sum of two quotients with an h on the bottom. So let's go ahead and do that. We still have a limit as h goes to 0. This is going to be a v of x. You still got the u of x plus h here, minus u of x, all over h. Plus, I can write the limit here because, again, it's a sum with the same denominator. Limit as h goes to 0. And we have another quotient here. This is u of x plus h outside of v of x plus h minus v of x over h. Okay, so, well, there's a little h here that's just from the stuff above. But you can see that for this step here, I now have two different limits, right? There's a limit here and there's a limit here. And one thing that I want you to notice is that, in fact, look, this part right here with the limit is really a difference quotient in u, isn't it? So I can write this as the derivative of u, right? This is u of x plus h minus u of x over h. Well, that's u prime. So this is actually u prime. U prime of x. That's what that little green box is there. And similarly over here, look, this is also the same thing. You get v of x plus h minus v of x over h. Guess what? This is also a difference quotient. And so if I put the limit with this, this gives me v's derivative at x. So actually, I've got some quantity here, u of x plus h, multiplied by the derivative of a v. And over here, I've got some v multiplied by the derivative of u. This looks very much like the product rule. So let me write this in a more, well, coherent way. And you can see that exactly we've proved that the product rule will work for any generic function defined as the product of two other functions, u and v. So now I've rewritten what we came up with. That is, I've got the sum of two limits, right? So the first one has this v of x out here with this difference quotient. And the second one has this u of x plus h with a difference quotient. So the key thing to keep in mind is that we only worry about h. So this v of x can actually just be factored out of this difference quotient. And similarly here, if h goes to 0, well, the h just goes to 0, and this becomes just u of x. So this comes out of this limit as just u of x. And so essentially I can rewrite these in the very end as this is going to be v of x. Again, when you put the limit in front of this difference quotient, it's just a derivative, right? That's exactly how we define the derivative of a function. It's just that instead of f, we have u. And similarly here, when this comes out, you get u multiplied by this difference quotient with a limit. And again, it's the derivative of whatever this function is. In this case, it's called v. So this is, again, v of x multiplied by u prime of x plus, this is going to be just u of x, because again the h goes away there, multiplied by the derivative of v. So this is v prime of x. And so I've just proved to you by using the definition of derivative that in fact the product rule really works. And this works for any function defined as the product of two other functions. Call them u and v. Now let's look at some examples to practice the product rule. Okay, now that I've proved to you how to differentiate the product of two functions. We just have to identify the pieces. So here's the first one. The first one is a function of x. So Think of it this way. I can identify that this is really my u of x, and this is my v of x. Okay? So remember the product rule. It says that if I differentiate f, I've got to, each one of these functions, each one of the constituent functions gets its own derivative. Remember, we want to be democratic. And then we just add the result together. So again, it doesn't really matter which one we do first, because in the end, we just add them. So remember, we do, well, the product rule is u prime v plus the other way around, u v prime. Okay? And so let's go ahead and do that. Again, we differentiate the first one. We ignore the v for now. So if I differentiate this, remember we're going to use the sum difference rule and the power rule. Okay, we know how to differentiate polynomials now. X can be written as, well, root x can be written as x to the 1/2 power, right? The derivative of 2 is 0 because it's a constant. So if I differentiate this, I get 1/2 x to the, well, 1/2 minus 1 is minus 1/2, plus 0, so I won't write that. And that's multiplied by v. Well, v is just x squared plus 1, plus the other way around. So I just rewrite u. Here's u. It's root x plus 2. Multiply that by the derivative of v. Well, again, this is a polynomial. The derivative of 1 is 0, and the derivative of x squared is going to be 2x. Right? Bring the power down, reduce the power by 1. And now we sort of expand this as much as possible to simplify it. So what do I get here? If I expand this part, I'm going to get, well, let's see. For the first term, it's going to be x squared multiplied by this quantity. So I'm going to get an x squared over 2 root x plus just these two multiplied by one another. So I get a 1/2 x to the minus 1/2 plus, if I multiply this 2x by this sum, I'm going to get 2x root x plus 4x. And we can simplify a little further to get these things into single powers of x. Of course, this is the same thing as, remember this is downstairs, so this is like a minus 1/2. So 2 minus 1/2 is what? 3/2, right? So this is going to be x to the 3/2 power over 2 plus, well, we can leave this as 1 over 2 root x. Sometimes it's nice to get rid of the negative exponents. Plus, well, if I want to write this as a single power, well, this is x to the 1/2 power multiplied by x to the 1. So we add the exponents when we do that, when we have the same base. So this is going to be 2x to the 1 plus 1/2 is 3/2 plus 4x. Okay, so that would be the simplified version of the derivative here, just using the product rule. So now let's look at the second example. Now we have a function of y. And again, we just do the same thing. We identify the pieces and we differentiate. So notice that since this is a function of y, u's derivative with respect to y is we just differentiate this term by term. So this is going to be, again, we have power rule again, except now the powers are negative. The negative 2 comes down, reduce the power by 1. The derivative of the second one, the same kind of thing. The negative 1 comes down, reduce the power by 1. And we multiply the result by v of y, which is given here. This is 2y to the minus 3 plus 1, plus the other way around. Now u of y is here. This is y to the minus 2 plus y to the minus 1. And I multiply that by v of y. V prime of y, I should say. So I differentiate this. Again, the derivative of 1 is 0, so all I've got is this one term. So again, the power comes down. I get a minus 6y to the minus 4 power. Reduce the power by 1. And we can go ahead and simplify this as far as possible, but ultimately, this is the product rule.